So, we have been discussing memory BIST. So, memory BIST stands for memory built-in self-test. And it is mainly used for SRAM and possibly DRAM also. See, embedded DRAM is not very common. And it is meant for embedded memories. So, like I was saying, if there is a big chip, there could be a number of memories M1, M2, M3, M4. So, usually there will be one controller called as a P-BIST controller. This is programmable BIST controller, and it can be programmed by the when I say programmable, it means it can decide which algorithm should be used. Like, should we use March B or March C minus? So, when they are diagnosing memories, if they find that lot of memories are showing failures and so on, there may be a need to go back and look at what is wrong. So, maybe more extensive algorithms may have to be run. So, that is why it makes sense to have a programmable BIST controller. Okay. So, this is a P-BIST controller. I think now this has become very standard. In the early days, they used to possibly have many BIST controllers. There may be one controller here and there is another controller here, and this controller is responsible for some of the memories here. There is another couple of memories for which this guy is responsible. But I think it is now more or less standard to have a single programmable BIST controller. And self repair is also included, meaning memories come with extra rows and columns, and when faults are found on certain rows, okay, so you can decide that this whole column can be eliminated and a extra column can be used in its place. And similarly, maybe there is a row here that you can eliminate and a row here that you can eliminate, and another row here and another column here. So, you will possibly use extra column for this, extra column for this, extra row for this, and extra row for this. So, by doing this, okay, so these are your extra rows and extra columns. There are other ways to handle memories. When there is a fault in the memory, right, people have used what are called as Hamming codes. To detect errors and possibly correct one or more errors. So, these are based on parity. What is parity? Suppose I want to store the value 10110110. Okay, this is the 8-bit data that I need to store. So, we count the number of ones. So, there is 1, 2, 3, 4, 5, 5 ones. So, if you are using even parity, then the number of ones should be 0. I am sorry, even. Okay. So, we have to add an extra 1 to sort of make the parity even. So, 8-bit data can be supplemented with 1-bit parity. And then another example 10111100. See, here also there are 1, 2, 3, 4, 5 ones. So, we will store a 1 in order to make the parity even. In another case, it could be 00111100. See, it is already even parity. So, we have to store a 0. So, a 9-bit data instead of 8 bits. See, this is even in ASCII code it is done. So, what is the advantage? You can detect possibly some errors. Okay. If only one of the bits changes value, for example, let us say this because of some reason has become 0, right, then we know what the parity bit is. We were expecting even parity, but we are seeing 1, 2, 3. So, something must be wrong. Okay. So, can detect one error, but we do not know what, I mean whether it, which bit is bad, we do not know, right. And if multiple errors happen, it will fail. Okay. See, for example, if 2 bits become zeros, then the parity will not be able to detect that there are 2 bits which in error. Okay. For example, if you get 00110000, this parity also looks good. It is an even parity and this is storing a 0. So, looks good. So, we assume that it is good, but actually there is an error. So, memory error, these are called error, this is called error detection. By adding more bits, by adding more parity bits, we can not only detect that there is an error, we can detect where it is. So, if we know that the error is at a particular position, then we can correct it by flipping that bit. See? So, that is called as error correction. So, obviously, many parity bits will be required, one will not do. With one parity we can detect maybe one bit error, but if you want something like error correction, right, then you will need many more parity bits. So, these error detection and correction were originally invented for communication. So, when we communicate data, things may go wrong. For example, we may have stored the data on disk. When we read and bring it to CPU, maybe something went wrong. A 1 became a 0 or something like that, or a 0 became a 1. So, that is what it was originally intended for, but now it is being used. So, error correction codes are now also used with memories. These are called ECC memories, error correcting memories, error correcting codes memories. So, these are error correcting code is ECC. So, it is common to say ECC memory, which means it is a memory in which data is enhanced with some code, with error codes, error correcting codes. So, here it is shown for 4-bit data, okay, 4-bit data. So, let us say these are the data bits, these are originally they were not called D7, D6, originally they would have been called D3, D2, D1, D0, right. But we have added some parity bits, okay. In this case we have added P1, P2 and this also. So, as I told you, for 4 bits of data, if you want to be able to correct the data, you will need as many as 3 parity bits. See, it is like almost doubling, right. Instead of 4 bits of storage, we have to use 7 bits of storage. So, these are labeled 1, 2, 3, 4, 5, 6, 7. Okay. The parity bits are placed in 1, 2 and 4. Why are the parity bits being selected to be placed in 1, 2 and 4, right. See, if you write down 1, it is 0, 0, 1. If you write 2, it is 0, 1, 0. If you write down 4, it is 1, 0, 0. Okay. So, that is the reason why we have chosen these positions. And the data is fit in the remaining. Okay. So, we label the things as so, let us label them as 1, 2, 3, 4, 5, 6 and 7. So, as I told you 1, 2 and 4 are special. 1 is 2 to the power 0, 2 is 2 to the power 1, 4 is 2 to the power 2. So, these guys are special and we will call them as parity 1, parity 2, parity 3. Okay. The remaining one will be data. Okay. So, in this picture they have decided to call it as D3, D4, D5, D6 etc. Okay. Because 1, 2 and 4 are already taken. So, they have decided to call it D3, D4, D5, no D4 is not correct. Because they decided to call this P4. See, it is 1, 2 and 4. So, they called it P2, P1, P2, P4 and the data is called D3, D5, D6 and D7 because they are in position 7, 6, 5 and 3. Okay. So, they have gone purely by position. So, P1, P2, P4, D3, D5, D6 and D7. Okay. So, suppose the data that we have to store is 1100 or something like that. This is let us say 1100 and let us say we are using even parity. Okay. So, what is done is P1 is calculated as parity of all data elements whose index has a 1 in position 1. So, remember parity 1 is 001, right. So, this is 001, 1 means 001, 2 means 010 and 3 means 100. So, if you look at all positions where there is a 1 here, D7 satisfies that property because 1 is 7 is 111, 6 is 110, 5 is 101 and 3 is 011. So, wherever we have 1 we take those. So, D3, D5 and D7 will be taken. Okay. So, that is why it is written like that. So, this is D3, D5, D7 because these data indices 3, 5 and 7 have a 1 in this position. In the same way, look at all those data indices which have a 1 in this second position. So, that is 7, 6 and 3. Similarly, those which have 1 in the last position, that is 7, 6 and 5. Okay. So, we will take P1 is the we have to take 3, 5 and 7. So, 3 is 0, 5 and 7. So, we are seeing 100. So, if it is odd even parity, we have to put a 1 here. Similarly, P2 is D3, D6, D7. D3 is 0, so D3 is 0, D6 is 1 and D7 is 1. Okay. D7, D6 and D3. So, here also the we already have even parity. Okay. The green, whatever I underlined with green, so there are 1, 1, 0. So, it is already even parity. So, we have to put a 0 here. Then P4, it is D5, D6, D7. So, that is let us say we underline it in this blue color. So, the parity of 110 is already even, so we put a 0 here. So, we have added some extra bits and this is what will be stored in the memory. Now, when we read from the memory, it is possible that we receive some, maybe one bit has gone bad. Okay. So, let us say we receive 110 1001. Okay. This is what we received. Again this is D7, this is D6, we have this is what is stored and we are receiving like this D7, D6, D5, P4, D3, P2, P1 and I am saying that we are receiving one bit error. Let us say for the let us say D5 has flipped. D5 has flipped. P4 has remained same. D3 is 0, P2 is 0 and P1 is 1. So, we recompute the parity bits. Okay. Again P1 is nothing but the parity of, let us erase the P1, P2, P3. P1 is a parity of 7, 5 and 3. So, this is 7, this is 5 and this is 3. So, we are seeing odd parity. So, we will put a 0 here. Then the P2 is 7, 6 and 5, that is 7, 6 and 5. Okay. Wait, that is P4 I think, 7, 6 and 5 is P4. So, this has become odd parity. So, we have to put a 1 here. P2 is 7, 6 and 3. So, 7 is 1, 6 is 1, 3 is 0. So, already it is fine. So, we put a 0 here. So, the new parity bits are 1, 0, 0. The original parity bits were 0, 0, 1. Okay. If you XOR these two guys, you will get 1, 0, 1. And that is a error position. See, that is this position 5. See, this is the error position. So, that 101 means it is showing the error here. Okay. Maybe we will do another example. So, again let us write down 7 positions, call them 1, 2, 3, 4, 5, 6, 7. This is we call it as P1, P2 and P4, D3, D5, D6 and D7. Let us pretend that the value to be stored is 1, 1, 1, 1 and parity bits had to be calculated. So, 7 is 1, 1, 1, 6 is 1, 1, 0, 5 is 101 and 3 is 011. So, these are the data positions 7, 6, 5 and 3. So, wherever there is a 1, that is 7, 5 and 3. So, we have to take the 7, 5 and 3. So, here it is 1, 1 and 1. So, it is odd parity. So, we have to add 1 in order to make it even. What about the second bit position? We again see 7, 6 and 3. So, 7, 6 and 3 are also all 1. So, we have to put a 1. Finally, we have 7, 6 and 5. So, all of them are 1. So, we put 1. So, this is a special case, everything was already 1. So, though the actual data is 4 bits, we store 111111 7 bits. So, it is going to be expensive. We have 3 more bits to store. Now, suppose when we retrieve the data from the memory, one bit went wrong, let us say this 0 went wrong. So, this became 0. So, it is bad fault. So, again we compute P4, P2, P1 for the retrieved data. So, 7, 6 and 5. 7, 6 and 5 is, no, I am sorry, 7, 6 and 5 is P4. So, 0, 1, 1 it is already okay. So, this becomes 0. Then the second is 7, 6 and 3. So, 7, 6 and 3, 7, 6 and 3. So, 0, 1, 1. So, it is already good. So, we put a 0 here. The last one is 7, 5 and 3. So, 0, 1 and 1. So, again this is 0. So, I calculated this from the fetched data. Whereas, these were already fetched, this is already available to me. Now, I will XOR both of them, 1 and 0 XOR is 1, 1 and 0 XOR is 1, 1 and 0 XOR is 1. So, it is telling me that position 7 has a problem. So, that is what we had done, right, we had flipped 7. Okay. So, that is what is Hamming code. So, if this data, suppose we were going to store some 1024 bits, 1024 words, each was 4 bits. Now, unfortunately, it will be an additional 3 bits. So, we will need 1024 multiplied by 3 bits extra. That is overhead. Okay. In general, suppose there are n bits, and let us say we have to add m parity bits. How many parity bits do we need, right? See, if I write down in the previous example, I wrote 3 parity bits, right? Using 3 bits, you can have indices from 000 to 111. That means you can you can go up to 7 positions. Here there are m bits, so it can m bits can point to 2 to the power m positions. How many positions do we have? We have n plus m positions. So, your 2 to the power m should be at least greater than or equal to n plus m. So, for example, when n equal to 4, 2 to the power m should be greater than or equal to 4 plus m. So, you will find that m equal to 3 will satisfy this. So, 2 to the power 3 is 8, and on the right hand side we have 7. When n equal to 8, 2 to the power m must be greater than or equal to 8 plus m. So, m equal to 3 will not work, because on the right hand side we have 8, and on the left hand side we have 8, and the right hand side we have 11. When m equal to 4, we will get 16 on the left hand side and 12 on the right hand side. So, m equal to 4 will work. When n equal to 16, 2 to the power m is greater than or equal to 16 plus m. So, 2 to the power 5 will work. So, m equal to 5 will work, because on the left hand side we have 2 to the power 5 or 32, on the right hand side we have 21. Okay. So, you should know this, right, how many parity bits, and the algorithm is always same, right. We write down the positions 1, 2, 3 up to n plus m, right, and we decide where the parity bits are. The parity bits will be in positions like 2 to the power 0, 2 to the power 1, etc. So, these are the parity bits, and the data bits will be in the remaining positions. So, the memory will have additional m bits for every word. So, it is a little expensive, but we have no choice when it comes to very high demanding applications. See, suppose the application demands that you should not have any errors, like I was telling you yesterday about fault tolerance, right. I mean, I was talking to you about automotive, industrial, etc. See, there an error in memory may change everything, right. One bit is changed, maybe it results in a completely incorrect answer, right. See, if let us say there is some angle that we have calculated, and this was a 0 in the original one, but it became 1 in the error thing. See, that will change the angle completely, isn't it? So, your control, whatever you are doing, is gone, completely gone. The angle itself has gone bad. It could be the velocity, it could be whatever it is that you are calculating. So, one bit change can play havoc with your algorithm. So, having error correction codes, what we just discussed is single error correction code. It can only detect one error. and it will detect and correct one error, single error detection and single error correction. But if you are willing to have more parity bits, you may also be able to detect two errors and correct one error, things like that. So, but more parity will be required, and that is too expensive. So, usually people just have single error detection and single error correction. Okay. So, that is about having codes, and it has now become mandatory for automotive and such applications to sort of use these ECC memories. Okay. ECC memory means the memory has error correction.